Hello everyone. In this video we're going to talk about state observers in control. If you remember from my previous videos when I talked about controls in the state space and the pole placement method, which uses a simple control of u equals negative k times x, where x is the vector with all states of the system in it, so we call it full state feedback control. Right? The thing is, you have to have all states of the system measured and be accessible, right? And the problem is many times all of these states of the system are not accessible, or you don't have sensors for them, or if you do, the measurements are so noisy that they might not be super useful, and you have to do either a lot of filtering, which comes at a cost, and sometimes those filters values are not representing exactly the original values depending on how good your filter design is. So in those cases, those states that are not accessible or are super noisy, instead we might go with some estimation of them. We might estimate them if we have the model of the system correctly, if we have the dynamics equations of the system correctly, then we might estimate those values. And this is done using what we call state observers. So observers are estimators, okay? And those can be just in a computer. They can just be generated digitally. You don't need any sensors for them. So observers are good. They can save you on the money for sensors. They can save you from noises in the data. They can get you states that are not even accessible for measurements. The problem they have is they are good only if the models of the system are very accurate. So there is nothing like unmodeled dynamics, or the values of these parameters in ABC are also correct. If you don't have accurate measurements of the system parameters, then observers are not going to be really good unless you do the control called adaptive control, where you try to estimate also those parameters as well. And that is beyond the scope of this lecture. So here we assume that this model of the system dynamics is very good and accurate. And so the estimates we can have from the states are very close to the actual ones. Okay? So how do we do it? In the full state observer, we try to estimate all of the states of the system and use those estimates instead. So even if some of them we can measure, we are not going to do that. And instead of all of these x's, we use what? We use the x tilde, which is the estimate of x for all of them, whether we can measure or not. And so our control law, instead of u become negative k times x, now becomes negative k times x tilde. Okay, so our full state control is now going to be full observed state control. Basically, that's what it becomes. The question is, how do I get these x tildes to be equal to, or at least converge to the x as time goes on, make sure my computer estimations of the states are approaching the actual values, okay? How do I do that? That design is called observer design. How do I do that? So here, we assume that the dynamics of the system is given by x dot equals ax plus bu and y equals cx, and here we neglect the D matrix, the direct for input-output matrix. We assume this guy is what? Equal to 0 for this case, for simplicity, and the goal is to design an observer. And as I said, the goal of the observer is this x tilde over time will converge to x, and so there will be no error, okay? Because we define the error as the difference between them, so the goal is this error goes to what? Over time goes to 0. So how do we define the dynamics of this simulated system, this observer? The equation for the simulated observer is very similar to the equation of the system with some extra modification. So the dynamic equation, the x dot equal ax plus bu, now becomes x tilde dot equals ax tilde plus bu. You see, so far they are identical, plus an extra term. This extra term is the difference between actual output of the system y and the estimated output of the observer y tilde equals cx tilde. So you see the output equations are the same. Okay, so this guy here is the output error. Okay, it's the difference between what? Between actual output and estimated output. So this is like output estimation error. In Kalman filters, which going to be one of my future videos, we call this guy innovation term. So we multiply that also by a gain, and the goal of this gain, KE, is to control how fast this E will converge to 0. Just like the K, the goal of K was how fast those X's will converge to the final values, right? The goal of KE is how fast the estimation error E will converge to 0. So that gain is, we can tune it basically. So, and you can see that if X will converge to X, X tilde will converge to X, then Y tilde will also converge to what? Converge to Y. Therefore, this error term will converge to 0. So your observer equation will be the exact same thing as your system equation. And of course, this is when what? When X tilde and X are identical. Okay, so it completely does make sense. They become the same thing. Okay, so now we are going to what? We are going to expand this equation if you want. You can expand it or we can keep it as is. So if you expand it, this X tilde term appears in two places. One is AX tilde, the other one is K times C times X tilde with a negative sign. So if you factor it out, you can write it like that. And then the BU term stays, and then KE times Y, and Y is CX, is going to be this term here. Okay? So your X tilde dot is going to be A minus KEC times X tilde plus BU plus KECX. So this is the dynamics equation of the observer, and this is the output of the observer. Good? Now, how can we make sure that, as we said, this error converges to 0 over time? Let's see. So here we form the error by difference between actual state and the estimated state. And we look at the error dynamics, which is the time derivative of E. So if you take a time derivative of E, it's going to be X dot minus X tilde dot. For X dot, we plug it from here. So it's going to be A minus AX plus BU minus, and for X tilde dot, we use this guy here that we have, and we plug it right here. And if we subtract, some terms would cancel out. What terms? The BU term will go away. Then you have AX minus A tilde minus AX tilde. So it's going to be A. If you factor out A, it's going to be A times X minus X tilde. Also, if you look here, you have a KE with a double negative, so it's going to be a positive KEC, right? Or if you want to keep the negative, negative KEC. This guy is going to be negative X tilde, and then this guy is positive X. So if you factor out X minus X tilde, it's going to be A minus KEC times the difference. And remember, this difference is what? E. So it's going to be A minus KECE. This guy equals to what? E dot. And what kind of equation is this? This is a first order differential equation. If we choose KE such that this whole matrix A minus KEC is negative definite, right? If it's negative definite, then you can show that the solution of E will go to 0 because E will be a bunch of exponentials with negative powers. So E will go to 0. So all we need to do is to choose this gain matrix KE such that A minus KEC becomes negative definite, or the eigenvalues of this matrix are negative. So if the eigenvalues of A minus KEC are negative, still we can have what? The error to approach 0, and that's the ultimate goal. So how can we do that? We'll do it the exact same way that we designed the K for pole placement. Remember here, for pole placement, the goal was what? The goal was to make this matrix A minus BK be what? Negative definite. Remember, in this case, it's what? A minus KE times C. Instead of that matrix, you have this guy. How did we choose K? Remember, K, we found it using this Ackermann's formula, which was this vector of all zeros and 1 times the controllability matrix times phi of A, where phi is the polynomial with desired roots for the matrix A minus BK with the desired eigenvalues. So it was the characteristic polynomial of the new A matrix. Right? Now, exact similar thing, Ackermann formula, can be used to calculate KE, and that is what you can see down here. This time the order is different, so the phi of A comes first, then you have the observability matrix, and then you have this vector with a bunch of zeros and ones. So remember, this guy is what? This guy is the observability matrix. So can we always find a KE? Yes, as long as this observability matrix is full rank. Because look here, we need to invert it. So this guy has to be what? Full rank. In other words, the system has to be what? Observable. If the system is observable, this matrix is full rank, the inverse of it exists, and we can always find the gain matrix for the observer. Similar thing that we did here, remember, we could find this K when this matrix, the controllability matrix, was full rank, because again, we needed to invert it. So this controllability matrix, remember, this controllability matrix, it had to be what? It had to be full rank, right? Which means the system was controllable. So if the system was controllable, we can find a controller gain. If the system is observable, we can find an observer gain. And finally, when we find the observer gain, then we form our observer using these two equations. We form our observer, our computer simulation observer, using these two equations, because now I have KE, A and C and B come from the system. And so we have to have accurate estimate of them. And this observer will give us X tilde that, as I said, we use to form what? U. So once we have this X tilde, we send it to a gain block of K, and the result is going to be what? Is going to be the input, the control input U, which not only has to be used in the physical system, it also has to be used in what? In the observer. So this is the diagram of a full state observer, a full state controller with full state observer. This guy down here is your full state observer. Inside this box. And this guy is what? This guy is your full estimated state, right? Controller. So without any sensor, if your dynamics models are very good and your parameters are good, you should still be able to control the system. Okay? So this is called full state observer, full state controller. By the way, here you see you have integrators, and integrators need initial conditions. Okay? So the question is, do I need to use the same initial condition of the system? Do I need to use the same ones for the observer? The answer is no, you don't have to. So if you use different initial conditions for the observer compared to the system's still gonna work. The controller is still gonna work. Okay? And I'm gonna show you right now using a Simulink model that I developed. But first, let's look at the example related to the Simulink model. Let's talk about this example. Let's solve it on basically we call paper, and then I'm gonna show you the system. So here is the example. Here I have a physical system. These are the fundamental matrices, ABC. As I said, D is 0. We want to use a full state observer to control the system where the poles of the observer or the eigenvalues of the A minus KE times C matrix are at -10 and -10. And the poles of A minus BK, the controller matrix, are at -2 and -2. Okay? And one thing that is very important, and I need to mention, I highlighted for you here, is the poles of the observer should have bigger negative values compared to controller. In other words, the error dynamics of observer should be several times faster than the controller. Why? Because if these estimated values that I'm sending to the controller, they are not very close to the actual states, then your controller is sending wrong signals to the system to control it. So these X tildes that I send to the controller should be very close to the X. And for them to reach X before the X reaches the final value, these guys should have bigger poles in magnitude, bigger negative poles. So you see here, as I said, at least 5 times faster. If my poles of the controller are at -2 and -2, my observer are -10 and -10. So first the observer will converge to the actual states, then the controller will make the states control to the final values. Okay, so please keep that in mind when you choose these poles. The observer poles should have at least several times bigger magnitude, and they should all be negative, of course, for stability. So now the question is, how much is KE and how much is what? K, and we go and use those formulas that we had. This formula here is what? This formula, we use it for KE. Remember this formula here? So we're going to use that for KE. And this formula up here, we are going to use what? For K, this one. So let's go ahead and use them. So in this case, we need to form phi of A and then CA, C and CA. So phi of A for the observer is what? For the observer, phi of A is basically what? It's A minus mu1 times I times A of minus mu2 times I. And I is an identity matrix, the same size as A, right? So this is the desired polynomial for this guy, and a very similar thing for this one. It's the same thing, but mu's are different for controller. Okay? So if you want to go for the observer design, your phi of A is going to be A minus 10i times A minus 10i, right? So for observer, phi of A is going to be, again, we used negative 10 and 10. So it's A minus minus 10. It's going to be A plus 10. Sorry, it's going to be A plus 10i times A plus 10i. So it's going to be A squared plus 20a plus 100i. I of 2 by 2, of course, because this is a 2 by 2 matrix A. So that is what? That is phi of A. And then we need to form the observability matrix C and CA. So we have C and CA, and C in this case is 0 and 1. And if we multiply it, pre-multiply it by A, so 0 and 1 times that, okay, you're going to get a 1. And then 0 and 1 times this guy is going to be 0. Yes? So we multiplied that by here. We get the 1. We multiplied by this one. We got a 0. So that's the observability matrix. Clearly, the determinant of this guy is negative 1, so it's invertible. And finally, times 0, 0, 1. Okay, so we need to form this. We need to form this. And then multiply it by 0 and 1. So this guy is multiplied by that one and by that one. And if we do and simplify, in this case, you are going to get 120.6 and 20. So this is what? This is your observer gain. 120.6 and 20. And then for controller, if you want, for controller, we need phi of A again, but this time the mu's are negative 2, negative 2, so it's going to be A plus 2 squared. So it's going to be A squared plus 4A plus 4 times I. And then we need the controllability matrix. Remember here, the controllability, this guy, B and AB, and we need to invert it and then multiply it by a 0, 1 from the left. So if we go back here, we need B and AB. And in this case, if you look at B, B is 1 and 0. And A times B, if you multiply these two by that, you get 20.6. If you multiply the second row by B, you're going to get a 0. Again, here, this guy has a determinant of negative 20.6. It's invertible. So now I multiply this 0 and 1 by this guy and then by this one. Okay, like that. Of course, by the inverse of this. And in the same, the previous case also, the CA, you have to invert it and then multiply it. Remember, it's the inverse of those matrices. And if you do that, then the gain of the controller K is going to be 24.6 and 41.2. Okay, so it's going to be a row matrix. So that is your controller gain. This is your observer gain to achieve 5 times faster dynamics. And here is my Simulink system, which I'm going to be sharing it with you. Here is my physical system, as you can see. Right? So here I'm exactly doing this model. Look, I'm exactly doing that. Right? Do a little bit of cleaning. Here we go. I'm doing exactly this guy. Okay, what do I have here? You can see that in the system, I have B times U, A times X are added, and then that is equal to x dot. You integrate x dot, you get x, multiply c by x, you get y, huh? So that is your physical system on the top. And here is what I have. U times b. This guy here is x dot. You integrate it, you have to pass to it two initial conditions. Here I use 1 and 1. And this is the C matrix, as you can see. This is the A matrix. And this is the B matrix. So the system will get U, will pass you Y. That's our system. The observer will get Y and U, and it gives you X hat. And X hat is passed to the controller, so it's multiplied by the K matrix that we just derived. Of course, negative K times X. Remember, your controller is negative K times X. That generates U that can be passed back to the system and the observer. So remember, U is negative times Kx. So here you have to put a negative here, okay? It's negative K times X. Pay attention to that. And so, what is our observer? You see the observer takes Y, subtracted from Y tilde, which is Cx hat, and takes that error term. Error is multiplied by error in the output, not error in the state. Error in the output. Multiplied by Ke, right? So basically, it will form this guy for you, right? Let me bring it back. It will form this term for you. Also takes U multiplied by B to get this one. And that's this signal, and then add it to A times X tilde, this one. So this guy is the X tilde dot, and integrate it to get X tilde, and as I said, this guy is X dot. Okay, so if you look, this is our observer. You can go in. That's B times U. This B1 is the same as B, it's just copy of that. Y comes here with Y hat subtracted. That's the error that I also want to monitor. This is the X hat goes to controller. This is the X hat dot. If you want, you can add here X hat dot. Right? And integrate it to get you X hat. And these are the initial conditions for X hat. You see these numbers 0.5 and 0.2, which I used, are different from the system initial conditions, which are 1 and 1. Okay, so that's another thing I mentioned for you here, that the initial conditions of the observer and the system do not need to be the same. They can be different if you want. And that's what I did here. And I'm sending my Y output and my error in the estimation. I'm sending them to an oscilloscope, and I'm simulating for 4 seconds, and I want to see how the error in the observation goes to 0 and how the output of the system in this case will go to 0. In this case, my steady state is 0, okay? I don't have a constant or anything. So here is the simulation, right? Let me simulate it for you. By the way, it's very fast. And you see here I use the subsystem blocks to organize the system better. And this is what you can see. Y is the yellow curve and error is the blue curve. And as you can see, the error converges to 0 way faster than the output of the system does. Okay, and that is because of using -10 and -10 instead of -2 and -2. So that was full state observer. Now sometimes you have some of the states available for feedback, and they are good signals. They don't have a ton of noise, and so you would rather use them instead of just estimations, the accuracy of which depends on how good your model is. So can I have a mixture of some of the states measured, some of the states estimated? Yes, that is called what we call a minimum order observer. So here your state vector has two components, XA and XB, where XA are the ones directly measured and XB are the ones like tildes that are estimated. And in this case, the system dynamics equations, vector x dot is going to be some A matrix times x plus some B matrix times U, and y here is simply 1, 0 times xa and xb, which basically means it's the same as xa. So in this case, the output is equal to those states that are only measured, not the estimated ones. So that is your C matrix. And your A matrix, as you can see, it has 4 sub-matrices, AAA, AAB, ABA, and ABB, and B also has BA and BB, depending on they are multiplied to which one of these states, the measured ones or the estimated ones. If you expand it, the dynamics equations for those states that are measured are going to be like this. If you expand it, xa dot equals AAA times XA plus AAB times XB plus BA times U. And for estimated ones, XB dot is ABA XA plus ABB XB plus BB times U. Okay? So these are the dynamic equations for those. And what about the output equations? Well, let's take a look at the output equation. So the output for the system is clear, y equals xa. What about the observer? What is the observer output equation? So for the observer output equation, this is how we define it. Y tilde, the output of the observer, which has to be compared against y to get you that output error term and multiplied by KE. This guy, we define it as AAB times XB, okay? This guy times XB. We just define it like that. Or, instead of that, that's this term here. If you want to get that, you take these 2 other terms to the left side. They become negative. So that term becomes xa dot minus aaxa minus bau, and that is what you can see over here. So we define our y tilde like that, and that is the output equation of the min state observer, this one. Why do we define it like that? I'll show you in a minute when I go over this table. And the way we define it is to make sure, again, the error dynamics converges to what? To 0. Okay, so this is my output equation for the observer. This is the dynamics equation for the observer, these 2 together. And then this guy here in blue, as well as this one, are the system equations. So now if you compare a min state observer against a full order observer, you see a lot of similarities. What are the similarities? Let me show you. So in a full state observer, the estimated state was x tilde, all of them. In this case, we call it xb or xb tilde. Okay? Now, XB are those states that you estimate. Their estimations, we call it XB tilde. The fundamental matrix you had was A. Here is ABB. As you can see, it's ABB that is multiplied in observer. Remember here, if you look at the observer equation, look at that. X tilde dot was A times X tilde. Here is what? Here is XB tilde dot equals what? ABB times XB tilde plus something else. So that ABB is the same as A. Then the BU terms that you had in the observer equation, this second term here, look, that second term BU that you have is now what? Let's go and see. It says the second term is now ABAXA plus BU. Where is that? That's these 2 extra terms, here and here. Okay? What about the output? Output of the full state observer was called y tilde. Here is still called y tilde, but it's equal to what? To x dot a minus aax minus bbu. So that's what you can see. The C matrix back there was just called C. Here, the C matrix is what? AAB. Okay, because in this case, Y tilde is what? AAB times XB tilde. Okay, so it's going to be like that. So if instead of those, you use these guys, you can still what? You can still go ahead and design your observer. So what was the equation? Remember, the equation we had was KE, right? Look at that Ackermann formula. KE was what? Remember we have it? Is that KE here, right? So let me grab it and bring it down. So I can still use that if I do my proper replacements. So I can still come here and paste it here, right? Look. But wherever I need A, I replace it with what? With AB, B. Wherever I need C, I replace it with AA, B, and that's it. So in this case, for full state observer, my error dynamics will be this. This is going to be the matrix that you will have for KE, as I said. And the observability matrix is this guy, which has to be full rank. And this is the formula for determining what? The Ackermann formula for determining the observer's gain. Okay? So we can use those, and that is going to be perfect. By the way, before I finish this, I just remember I need to say one more thing for you, and that is this part. So you might say the observer's values are used in controller. So you saw that I determined the KE and the K matrix completely separately from two separate formulas. And the question is, would they affect each other? I mean, when we change the gains of the observer, would that mean we are also changing anything about the controller? And the answer is no. And you can see that through these equations here. This is the back to full state observer, but if I rewrite my system dynamics equations with the controller, which is A minus BK times X plus BKE, and my estimation error dynamics, which is E dot was A minus KECE, if I combine X and E into one vector, and if I write these two dynamics equations, these two first order ODEs, in terms of a matrix format, then the derivatives will be this matrix times what? Times the vector itself. And if you look at this matrix, it's upper triangular. There is this component of all zeros. In other words, in E dot, there will be nothing about X. So controller will have no effect on what? On the estimator, the observer, and vice versa. So you can separately assign the controller poles from what? From the observer poles. And if you choose one of them, the other one can be independently selected, and it has no effect on it. Okay, so observer dynamics is isolated from the controller dynamics. And that's the same thing for a minimum state observer, a minimum order observer. Okay, so I just wanted to clarify that for you. So in this video, you learned full state observers and minimum state observers and how to use them with a full state controller to achieve regulation in a control system. Hopefully it was useful to you. I'll see you in the next video. Thank you.